ship zooming through.
All right, this is the last quiz of the week, and so there should be sent home a quiz for you to take. It will be Friday. That's the only work you have to do Friday. Just take the quiz. There is a back side of the quiz. Just ignore it. I'm going to send it back home with you next week to take the following week. But do quiz number 25. Do not do quiz 26. You won't be able to do it. Well, you might. It would be amazing. It is not open book. All right? No cheating. All right? So, again, I need a parent to please sign off that you did not use your book. It is not open book. Okay? But here's the little review for it. You'll want to know what the radical sign is, the radicand, what the index is. You'll need to know it's from lesson 8.1 to 8.3. You want to know what it would be a like term for a certain radical. All right, they have to have the same radicands. Then what a principal root is. Make sure you know that. And then how to simplify what we've been doing. There's adding and subtracting of radicals, just finding the square roots, etc. So, all right, so that quiz will be on Friday. Take the quiz Friday, you're done. All right, but for this lesson, let's do a little bit of it. On page 289, all right, 289, we'll be rationalizing the denominator. All right, rationalizing the denominator. Turn to page 289, please. And we'll begin to read. I forgot to erase the board from last time. All right, so we're definitely not multiplying radical expressions. We're done with that. Hopefully you did well on that work that I assigned for you to do. Rationalizing the denominator. Let's read it. One of the criteria for a radical to be simplified, as shown in the previous section, is that all factors raised to the same power as the index must be extracted from the radicand. In other words, x cubed is equal to x squared times x, which you just take the x squared out. X squared times x squared is x. Two additional criteria are that the radicand must be an integer and that a radical may never be left in the denominator of a final answer. In other words, the fraction must have a rational denominator. So you can never end with a denominator being a radical. All right? So no little radicals in your denominator. So when you're dealing with this, if you look there in the next paragraph, when the radicand is a fraction, applying the quotient rule allows the numerator and the denominator to be examined individually. If the radicand in the denominator is a perfect square, the expression results in a rational denominator. The illustration they give you is the square root of 7/4. All right? I'm going to write that on the board. The square root of 7/4. That is the same thing as the square root of 7 over the square root of 4, which we know square root of 4 is 2. All right, so we're able to eliminate that right there. All right, now that would be, all right, that's a fine answer. But remember, we have like x over 2. You could put 1 over 2 times x. All right, like if you had x over 2, that's the same thing as 1 over 2 times x. Whatever letter is on the top, you can always slide it over. That's how they got that answer on your paper. You had the square root of 7 over 2. Just treat it like a letter. A radical sign can be treated like a letter. All right, next line says, if the radicand denominator is not a perfect square, the irrational denominator will need to be rationalized. All right, so the square root of 8 over 3, the square root of 8 over 3, is equal to the square root of 8 over 3, which would be equal to 2 times the square root of 2 over the square root of 3. Now, what does that mean? So, again, if you look at the board here, we have the square root of 8 over 3. It equals the square root of 8 over the square root of 3. We're able to solve the 8. We look for a perfect square root. 4 times 2 is 8. So the square root of 4 is 2. So I have 2 square root of 2 over the square root of 3. Now we're not allowed to have a radical as a denominator. So the way to get rid of that is by, again, with any type of equation, and you treat a division problem, a fraction, like an equation. What you do to one side, if you do to the other, it keeps all things even. So if I want to get rid of the square root of 3, I'm going to multiply it by the square root of 3. Because the square root of 3 times the square root of 3 is the square root of 9. The square root of 9 is equal to 3. But whatever we did to the bottom, we got to do to the top. So I go back up here. If I multiply that times the square root of 3, I got to do that. Now 2 square root of 2 times the square root of 3 would equal 2 times the square root of 6. All right? Then when I come down here, I have 2 square root of 6 over 3. Or you could write it as 2/3 times the square root of 6, but both of those are the same answer. All right? So all you have to do to get rid of a irrational fraction or irrational number at the bottom or a radical, you can't have a radical at the bottom. All right? You have to eliminate it. You multiply by itself. You're able to get it. If you look at on page 290, all right, the illustration they give you, 290, it says simplify each radical expression. The first one they give you there, square root of 9 times square root of 64. All right, and so again, the square root of 9 is 3. Just look at your book. I don't need to write this out. Square root of 9 is 3. The square root of 64 is 8, so 3/8. All right, pretty simple. At the bottom, the next one, letter B. 3/8, the square root of 3/8 is equal to the square root of 3. Let's do that one, all right? 3/8. The square root of 3/8 is equal to the square root of 3 over the square root of 8. I can't do nothing to the square root of 3, but I can do the 8. 4 times 2 is 8. The square root of 4 is 2. So 2 square root of 2. Now, I have to get rid of that radical. So to get rid of a radical as a denominator, you multiply it by the radical. Okay? So I'm going to multiply each. Once you do one, you have to do the other times the square root of 2. Which equals now, 3 times 2 is the square root of 6 over 2 times the square root of 4. The square root of 4 is 2. So I have 2 times 2, the square root of 6 over top of that. 2 times 2 is 4, square root of 6 over 4. Or, again, you can make that 1/4 square root of 6. All right, so it's not, too difficult at all, I don't think. All right. If you have to do the same thing with letters, it works the same exact way. All right. The key to this whole lesson is you never want a radical as the denominator. Letter C gives you x squared over y, the square root, which means it's square root of x squared over the square root of y. Square root of x squared is x over the square root of y. I can't have the square root of y, so I'm going to multiply it times the square root of y. Alright, which leaves me with x times the square root of y over the square root of y squared. The square root of y squared is y, so x square root of y over y. Alright, that's it. So, I really think you'll be able to do that. We'll read the next paragraph there before we get going. Remember that, page 290, the purpose of the multiplication is to complete the denominator radicand by making it a perfect square. If instead of a square root, the denominator radical is a cubed root, then the radicand must be made into a perfect cubed. For a square root, the radicand is only multiplied by itself, but obtaining a perfect cube is different. Consider the fraction, all right? So if we have to have a cubed root, it's a pain. All right, but to do that, you have 2 over the cubed root of 3. You're going to multiply this fraction by the cubed root of 3. That would just cause serious issues, all right? Notice what they would do there, all right? It doesn't help at all. So the cube of 3 is 27, not 9. So instead of multiplying by 1 using the square root of 9, the numerator and the denominator, all right, instead multiply by 1 using the cubed root of 9 in the numerator and the denominator. Generally, for a radical with the index n, the radicand must be made a perfect nth power or n power. All right, now that was a lot of confusing words for this. Look at the illustration down there. We have the cubed root of 5/8. All right? The cubed root of 5/8. Now that's the same thing as the cubed root of 5 over the cubed root of 8. The cubed root, and this one, it's a little simpler. The cubed root of 8, there is one. All right, what is the cubed root of 8? What times what times what? 3 times give you 8. It's 2. All right, so this one is simple. All right, the cubed root of 5 over 2. And you're done. That's good for that one. All right, but what I want to show you now is if we have letter B, that example. Okay, so look down at letter B because this is the one you have to pay attention to figure this out. All right, so letter B says, all right, the cubed root of 8/5. That's the same thing as the cubed root of 8 over the cubed root of 5. Now the cubed root of 8 we know to be 2, because 2 times 2 times 2 is 8. Now the cubed root of 5 we can't work out. So what we need, all right, what we need then is we're going to have to multiply it by something to eliminate it. All right, so what would we multiply? So basically, I need to get a cubed root. So 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is 125. So I need it to be the, I have 2 at the top, I need it to be the cubed root of 125, because I know the cubed root of 125 is 5. So what do I have to multiply times the cubed root of 5 to get that? I'd have to multiply the cubed root of 25. And what I do there, I'd have to do there too. All right? 2 times that too. So what I do to the bottom, I have to do to the top. Now again, I'm going to pause. I need it to be a perfect cubed root. Here's the little Brother Burke shortcut. All right? Whatever this is, multiply it by itself, and that's what you have to multiply it by. So 5 times 5 is 25. Now if I multiply 5 times 25, I get a perfect cubed root. All right, so just multiply it by itself. There you go. All right, so when I do this now, I have the cubed root of 125 times 2 times the root of 25. All right, and then what is the cubed root of 125? We know it to be 5. 5 times 5 times 5. So now I have 2 times the cubed root of 25 over 5, and now I'm done. That's my answer. Right? So you have to eliminate if it's a cubed root. That's the only part that's a problem. It isn't that difficult as long as you catch my shortcut. All right? I need it to be whatever this is multiplied by itself 3 times to get a perfect cubed root. So I needed it to be 125. So what do I need to multiply this by? Well, just take 2 more of those. 5 times 5 is 25. So I have 1 5, 2 5s. That's 3 5s. And so it gives me 125. I'll do another one. Let's go ahead and do... Okay, let's go on down the bottom of the page, 291. All right, and we're going to do some of these and call it a day. All right, so page 291, I'm just going to have you do a few of these. All right, they want you to simplify again. Just make it both the numerator and the denominator into a fraction. Make sure you don't have a radical in your denominator. All right, it's really simple. So number 1 says the square root of 9 over 64. Square root of 9 over 64, which is equal to the square root of 9 over the square root of 64. Square root of 9 is 3, square root of 64 is 8. So 3/8, right? So that one's easy. Next one is easy. Number 3, the square root of 3 over 25 is the square root of 3 over the square root of 25. The square root of 25 is 5. So the square root of 3 over 5. Or you could do 1/5 square root of 3. That's fine too. Number 5, all right, the cubed root of 1 over 6, all right? So I'm going to have the cubed root of 1 over the cubed root of 6. The cubed root of 1 is 1. The cubed root of 6, I can't solve that. So now I got to get rid of the cubed root of 6. So I need something that will be a cubed root. All right, so I can't multiply it times 6. That just gives me 36. So I have to multiply 6 times. Remember what I told you, multiply, if I'm doing a cubed root, it's 6 times 6. So 6 times the cubed root of 36. Because when I multiply this out, I'm going to have the cubed root is going to be 6. 6 times 6 is 36. 36 times 6 is 36, 216. So my bottom is going to be this cubed root of 216 is the denominator. Of the top, I also have to multiply this times the cubed root of 36, which is going to give me the cubed root of 36. The cubed root of 216 is 6. And the cubed root of 36 at the top. Obviously, I can't do 6 is not the cubed root of 36. And so it has to stay that way because 2 times 2 is 4, 4 times 2 is 8, but at 5, 5 times 5 is 25, 125. 3 times 3 is 9, 9 times 3 is 27, and 4 times 4 is 16, 64. So there is no cubed root of 36, so it's the cubed root of 36 over 6. All right. Number 10, if I want to get rid of number 10, it says 3 over the square root of 5. In this case, I just need to get rid of that square root of 5. So I'm going to multiply it times the square root of 5. What I did there, I got to go to the top. So now I have 3 square root of 5 over the square root of 25. The square root of 25 is 5. So I have 3 square root of 5 over 5. All right, you're just eliminating that denominator as being that. So, all right, should be relatively. I'm not going to give you a whole lot. All right, just do numbers 1 through 16. All right, 1 to 16. If you'll do 1 to 16, should be easy. All right, 1 through 16, and we'll call that a day as well. All right, 1 to 16. And if you have a question, just shout out at me. All right, have a good day.